Hi there. We talked today in class about separation of variables within the context of differentiable equations. What separation of variables is getting all the x's onto one side of the equal sign and all the y's onto the other side. That way we can take the integral of both sides with respect to their respective variable. So for example, in this problem where we have dy over dx equals 5e to the negative x over 2, we're going to be looking to get the x's probably over here to the right because that's where they're already located, plus it allows me to get this dx out of the denominator by multiplying both sides by dx. Okay, so now we have dy equals 5e to the negative x over 2 dx. And like I said, now that they are separated, we're going to be able to take the integral of both sides. We'll take the integral of the left side with respect to y, and we'll take the integral of the right side with respect to x. Okay. Technically, there's a number here. It's 1, right? So we're taking the integral of 1, which is y. The integral of 5e to the negative x over 2 dx. When you're looking at your blue paper, this looks a lot like number 3, which says e to the u du. So I'm hoping that this negative x over 2 can be my u. Okay, so when I take my du, derivative of negative x over 2 is negative 1/2 dx. And I can turn it into this 5 by first dividing the negative 1/2 over, which is the same thing as multiplying by the reciprocal, and then timesing both sides by that 5. So we have negative 10 du equals 5 dx. Okay, so the 5 dx is going to be negative 10 du, right. Negative 10 du, e to the, and the negative x over 2 is going to be my u. And now it definitely looks like that third rule, where we have if the integral, so negative 10, integral of e to the u is e to the u, my u is negative x over 2 plus c. And that's my answer. Okay, one step more complicated would be number 48, which number 48 in your book says x times y prime equals y. Okay, so I'm going to start with rewriting that y prime as dy dx, just so I can see my dx. Okay, so I'm going to multiply the dx to get it out of that denominator. Times dx to both sides, and so now I'm at x dy equals y dx. We're close, but there's still an x over here on the left and a y over here on the right. So I'm going to go ahead and divide this x over, and I'm going to divide this y over. So now I'm at 1 over y, because that's in the denominator, dy equals 1 over x, because again that's in the denominator, dx. Now I can take the integral of both sides. Okay, so looking at my blue paper, this looks a lot like rule number 2, which says integral of 1 over u du is the natural log of the absolute value of my u, my singular variable. And then plus c. Now if I wanted to solve for y, I would do that by undoing this natural log, and the inverse of natural log is e. And so I'm going to raise both sides of the equal sign, both sides of the equation, above e. E and natural log interact, and so we're left with absolute value of y equals e to the natural log of the absolute value of x plus c. So c has an interesting component to it here because this c represents any possible constant, right? Because we're solving for a general solution. General solution represents all possible solutions. And so because this c represents any constant, it has a black hole effect. It sucks in any constant that is near it or that is applied to it, right? If we times 6, so 6 times c, it would still be c. Or if we subtracted 3 from c, it would still be c. Or if we times c by a negative, it would still be c. It just sucks everything in. And so what that allows us to do is actually simplify this equation a little bit further. going back to our properties of exponents, if we had had two bases being multiplied together, we solve that by adding the exponents, right? So two like bases being multiplied together, we add the exponents. Well, right here I see that I have two exponents being added together, which means technically, originally, it was two of the same base with those exponents. And so I can go ahead and rewrite this as e to the natural log of the absolute value of x times e to the c. Again, two like bases, we add their exponents, and so those two added exponents, that's what would have occurred. So we're undoing that step. And then once more we have here e and natural log end up canceling each other out. So we're just going to be left with the absolute value of x. But here, this e to the c, again, the c it represents any constant. So we have e raised to any constant. Well, if I raise e to any constant, I'm still left with any constant, right? C sucks in that e, like a black hole. And then technically, we're allowed to drop those absolute value bars because this absolute value implies that there's a plus and a minus aspect to the opposing side of the equal sign, or the opposite side of the equal sign. Well, again, c sucks in those constants, right? C times a negative is still c. It's any constant. And so that c is going to suck in the absolute values, and we're going to be left with c times my x. And that's my answer. Okay, so the final one is actually one of your homework problems. It's number 62. Okay, which number 62 says dr over ds equals e to the r minus 2s. And they're asking you to find the particular solution. They say at the point 0, 0. Okay, so the initial steps are going to be the same. Get the r's to one side, the s's to the other. But here, I notice my r and my s are both exponents, and so that's going to have to be fixed. Before I can do any sort of separation, I'm going to need to split that in some way. And again, that's a property of exponents. Okay, if we have x to the 6th divided by x to the 4th, so two of the same base being divided, we subtract their exponents. And so it's similar to the previous problem. We're going to undo that step because here I have two exponents being subtracted, which means that originally it was two of the same base being divided. So that's what I'm going to do here. This dr ds is going to become two of the same base being divided. The top one having the r, the bottom one having the 2s. Okay. So now I'm good to go for splitting them. I'm going to go ahead and get this ds out of the denominator. So I'm at dr equals e to the r over e to the 2s. And then I'm going to divide this e to the r over to the other side. And so now we're at 1 over e to the r dr equals 1 over e to the 2s ds. And we can take the integral of both sides. Okay. Well, looking at my blue integral rules sheet, this looks like number 3, e to the u, although that e to the u is up in the numerator, and so that's going to be my first step here. So I'm going to go ahead and rewrite this as e to the negative r dr and e to the negative 2s ds. And so now I'm going to be able to apply that third rule. Okay, so here my u is going to be negative r, which means my du is going to be negative dr. Now I don't have a negative here, so I'm going to go ahead and divide that negative over. Okay, so we're going to have integral negative du, which substitutes in for that dr, and e to the negative r is going to be u. Over here, my u is negative 2s, which makes my du negative 2 ds. And similar to this problem where I didn't have the negative, I don't have that negative 2, so I'm going to go ahead and divide that over to the other side. I'm going to go ahead and rewrite this. We have negative 1/2 du going in for ds, and e to the negative 2s is u. Now what's important to make sure we've made a distinction here. It's important that we made the distinction that this u is negative r and this u is negative 2s. Those are two distinct u's, and so if that's going to be confusing for you, you could subscript this, make this u sub 1, u sub 2. You could, I mean, frankly, you could put another variable rather than u du. Whatever you need to do to make sure you've made that distinction for yourself. Okay, so here integral of e to the u is e to the u, and its u is negative r. And integral of e to the u is e to the u, and this one's u is negative 2s plus c. Okay, now this is, if you remember a particular solution, they gave us a point at 0, 0. And so you can plug that point in at any point to solve for c. I'm going to go ahead and plug it in here. So we're at negative e to the 0 equals negative 1/2 e to the 0. Well, e to the 0 is just 1. So we're at negative 1/2 times 1, which is just negative 1/2 plus c. And then I'm going to add 1/2 to the other side, and so we're at negative 1/2 equals c. And I'm going to take that, I'm going to plug it back into my equation. So I'm at negative e to the negative r equals negative 1/2 e to the negative 2s minus 1/2. And so if we were to solve this and we wanted it in terms of r, we might take a couple more simplification steps. For one thing, I notice there's a negative in all three terms, so I'm going to go ahead and divide that negative out. So I'm left with positive e to the negative r, positive 1/2 e to the negative 2s, and positive 1/2. Okay, to get the r out of the exponent, I'm going to go ahead and take the natural log of both sides. Natural log of 1/2 e to the negative 2s plus 1/2. That's going to allow this natural log and e, because they're inverse functions, to cancel each other out. So I'm left with negative r equals natural log. And then here I notice I have a common denominator, so I'm going to go ahead and combine those two terms, e to the negative 2s plus 1 over 2. And so then r is almost by itself. Last step, divide that negative away. So we get r equals negative natural log 1 plus e to the negative 2s, I just switched these terms, divided by 2. And there's my answer.